My name is Yannick Maus, and I will today talk about efficient randomized distributed coloring in CONGEST. This is joint work with Magnus Haldarsson, Fabian Kuhn, and Tigran Tonegin. So this paper is a classic distributed graph algorithms paper. So we have a communication network of computers, and the goal is to color this communication network such that adjacent vertices get distinct colors. The goal here is to color the graph with delta +1 colors, but delta is the maximum degree of the network. Note that with that many colors, it's very easy to solve the problem in the sequential world, because you can just iterate through the vertices in an arbitrary order. And when you add some vertex, you can always pick a free color. There's just one color that has not been used by one of the already colored neighbors. So what's the difficulty in the distributed setting? Well, in the distributed setting, one of these computers doesn't know what the network looks like. So it maybe just knows its own ID and the communication link to one of its neighbors. Then it can talk to the neighbor to learn a bit more about the network and talk a bit more to learn a little bit more. But at some point it has to output, hey, I'm blue, and everyone else also has to produce an output. So in this model, every vertex has to produce its own part of the output. And what you notice that it has for sure not seen the whole topology if your algorithm is fast, because information can only travel one hop at a time. And this setting is studied in the classic model called the local model, and it was introduced by Nathilineal in the 80s. So here you take such a communication network, abstract it as a graph on n nodes, and you keep every node with a unique ID set. Then the vertices can communicate through the edges of the graph. And this communication happens in discrete synchronous rounds. So in one round, the vertex can perform some local computations and exchange messages with all of its neighbors. And here, this is very unusual for people who come from a centralized setting, is nodes are not charged for their local computations. The local computation time is unbounded and does not influence the complexity measure. The time complexity is only the number of rounds until each vertex has produced its output. So this talk will not be about the local model, but we will use it because I will explain the state of the art in the local model and relate our results to this. But instead, and for that, let me move my picture here. We will talk today the results of this paper hold in the CONGEST model, which is the same model, but here the messages that vertices can send can only be small, so order of log n bits per message. So for example, you can fit the constant number of identifiers into one message, while the standard local model has unbounded message size. So what's known about the graph coloring problem in both of these models? But if we first look at deterministic algorithms, and since the big breakthrough from 1 or 2 years ago, we know that we have polylog time deterministic algorithms for these problems. And actually the polylog right now stands at log to the 5. And we also know such a complexity in the CONGEST model with a bit of additional work. And actually, what's interesting now, what do we know in the randomized world? First, if you look at the local model, there we know that we have a log to the 5 algorithm. And you can see the 5 here is the same 5 as up here. This is not a coincidence. While in the CONGEST model, and this has been known for 30 years, the state of the art before our work was just the log n round algorithm. And what we do in this paper is we come up with an algorithm for the CONGEST model, which also has complexity log to the 5. In particular, we should figure out why do we have the same 5 appearing in the randomized complexity as in the local, as in the deterministic complexity. And this is because all the randomized algorithms for graph coloring are the recent ones. And actually, this is true for many algorithms in the area for different kind of problems, not just for graph coloring, use the so-called shattering framework. So this framework has 2 phases. The first phase is a randomized process, and the second phase is usually a deterministic process. So in the first phase, in this so-called pre-shattering phase, for the coloring problem, we gradually color some of the vertices and then remove these colored vertices from the graph. And this process is done such that afterwards, the uncolored components are small. So connected components of uncolored vertices after this first phase are small. And the precise definition of small here is pretty technical, but for the sake of this talk, you can just think of they're of logarithmic size or polylogarithmic size. And then afterwards, one just takes a deterministic algorithm and applies the best known deterministic algorithm on each of these components. And then the complexity of the second phase is just going to be the deterministic complexity on small instances. So that's why you get this additional log here in these complexities. We will more focus on the left-hand side today. So this right-hand side, as I said, yeah, there have been a long series of papers improving this deterministic complexity, but our focus is going to be on the left-hand side. And the first paper that introduced this shattering framework for many problems in the area is this paper by Barenboim, Elkin, Petty, and Schneider, which provided a log delta pre-shattering phase for the graph coloring problem. Note that if delta is as large as n or linear in n, this is in total just still gives a log n round algorithm. And then this was later improved in the local model to square root log n. This was the first sublogarithmic algorithm for the problem. And then even further to a very fast algorithm that only takes log star n rounds to shatter the graph. So both of these latter algorithms do not work in the CONGEST model. But the good news is that with some additional tricks that I won't talk about today, actually this post-shattering phase does work in the CONGEST model. So all we need to deal with is this pre-shattering phase. And what do we do in our paper? Well, what we have in this paper is we have a fast degree reduction, which gradually colors some of the vertices of the graph until the uncolored degree of vertices is reduced to some delta prime, which is just some log to the 4. And we do this degree reduction fast. And then our full algorithm is basically, we first execute this degree reduction until the maximum degree is small. Afterwards, we use the shattering framework from Barenboim, Elkin, Petty, and Schneider. And then we use the post-shattering phase, which in total gives us a log to the 5 round algorithm. So let's look at the core building block of our algorithm. By far the simplest algorithm, randomized algorithm that you can think of, because our core building block is just you pick a free color uniformly at random from your list of available colors. So here we are in the situation that some parts of the graph have already been colored, and this vertex V doesn't have green, red, and purple as available colors anymore. And this algorithm simply picks, lets every node pick the color that is not used by one of the already colored neighbors. It's the simplest algorithm you can think of. And what has been known for a long time is that this algorithm colors the graph, even when you have delta plus 1 colors only, in log n rounds with high probability. And actually this Barenboim, Elkin, Petty, Schneider shattering algorithm is also just the same algorithm with small modifications, but the shattering algorithm that they have is also this very simple algorithm. What we show is that this algorithm is even more powerful than one can imagine, or what was believed before, I guess. And to get some intuition for this, let's first look at a warm-up. What happens if we want to color with 2 delta colors instead of delta plus 1 colors? And then we need one definition. This is the definition of the slack of a node. This is the number of available colors in the list of a node minus the uncolored degree. It's basically how much freedom is there. And if we color with 2 delta colors, then initially this slack is delta because you have 2 delta colors available, but at most delta uncolored neighbors. So you have a slack of delta. And this slack predominantly determines your probability to be colored, because the probability that a vertex gets colored is just the slack over the number of available colors. So at the start, this here is going to be 1/2. But now if you execute this algorithm for one step, then after the next iteration, your uncolored degree will be only delta half. But your slack doesn't disappear, because if you if one of your neighbors gets colored, they might steal a color from your list of available colors and reduce the uncolored degree, but the slack can never decrease. So in the next iteration, the probability to be colored actually increases. It's already 2/3, at least if you have concentration here, which you have if delta is large enough. And then in the next iteration, you have an even larger probability to get colored. And this is sufficient to show that after log delta iterations, the uncolored degree has reduced to this log to the 4. And now you can just run this to reduce the degree, and afterwards use the algorithm by Barenboim et al. To get a polylog-log round algorithm for 2 delta color. And we want to mimic this whole idea of this slide here, also for the setting where we have coloring with delta +1 colors. And for that, we also want to have a similar notion of slack and somewhere get slack. And for that, we need one a bit seemingly technical definition, but the details of this definition are not so important. The definition is the local sparsity of the vertex. It basically just describes how many edges, or which fraction of edges are missing between neighbors of a fixed node. Because if you have such a node and they're very sparse, many edges are missing, then what one can show is that if you just execute this very simple random color trie algorithm for one round, then many of these vertices in the neighborhood, which do not have an edge between them, get colored with the same color. And whenever this happens, your uncolored degree reduces by 2, but the number of your uncolored, of your available colors only reduces by 1. So you get 1 unit of slack whenever this happens. What one can show is that a vertex gets slack, which is proportional to its local sparsity. So if you have vertices which are sparse, so let's consider the set V sparse to be the vertices which have a sufficiently large sparsity, then you can just run this slack generation here. And afterwards, the analysis is the same as coloring with 2 delta colors. So if you only focus on sparse vertices, you can quickly reduce the uncolored degree of the nodes to log to the 4, and then run the algorithm of Barenboim et al. Later. And this is the core of what we do. And this is also somehow inspired by previous work. We decompose the graph into a set of sparse vertices and into many sets of very, very dense vertices. So these vertices are so dense that they're almost cliques. So each of these CIs here is almost a clique. And this is why it's also called an almost clique decomposition. A bit more formally, this V sparse only has sparse vertices. And each CI is roughly a delta or delta +1 clique. It has the number of vertices is very close to delta. And every vertex in such a CI has most of its neighbors also in the CI. There's still some edges, as you can see here, between these different parts, but not super many. So this decomposition has appeared in the literature in many, many different settings, in different versions, but we try to present it in an even simpler way than it was before. And But we can show that you can also compute such a decomposition with high probability in the CONGEST model in constant number of runs, at least if the maximum degree is large enough, sufficiently large polylog n. And given this decomposition, I can already state most of our algorithm, because our algorithm just has these 3 steps, or actually it's 4 steps. First, we compute the decomposition into sparse and dense almost clicks. Then we generate the slack by just running this very simple algorithm for 1 round, which gives slack to the sparse nodes. And then we color the sparse nodes by repeating, first reducing the uncolored degree by repeating the simple algorithm for log delta times, and afterwards using the Barenboim et al. Framework to color these small degree vertices. So everything that is left after step 2 here is that we need to color the dense nodes. But this is quite a bit more challenging, because if we for the dense nodes now would like to just take the same algorithm here, let everyone just take a random free color, then you would have many, many conflicts, because there are a lot of edges in these dense parts and the progress would be very slow. So instead, and this is also inspired at least by previous work, but our setting is a bit simpler and has in particular a much simpler algorithm, is that we synchronize the color tries within the dense parts. So when you have one of these almost clicks, consider this down here to be one almost click, then you synchronize the color tries in here such that the colors that all the vertices in here try are not in conflict. They all try distinct colors. But from the outside, it still looks like all the vertices in this almost click behave randomly and pick their color randomly. So this is really the goal that we need to implement here. We want to have this synchronous color trial. We want every vertex in an almost click. So on the right, what you see here, this is an almost click, to pick a random available color such that internally inside this almost click, no conflicts appear. And it's important here, we've already done a lot of coloring before in previous steps. So every vertex has some neighbors outside of the almost click or even inside the almost click that are already colored from this slack generation on the steps that we did before. So everyone only has a list of available colors here. But if we can do this, then we can show that the uncolored degree reduces again to log to the 4 quickly. And the complexity here is mainly this, but for the sake of this talk, ignore this log n factor, which is just a technicality, is mainly log delta squared. And this mainly comes because we do not 100% what I just told you, but we need to use the layering technique inside each almost click. So we process each almost click in log delta layers. But if you ignore this layering, then what we do is we just execute log delta iterations of the synchronous color trial inside each layer. And the analysis then shows that first, the external uncolored degree goes down fast, very similar to an analysis that we've seen earlier in this 2 delta coloring. And once this is small, also the internal uncolored degrees go down fast. The crucial property here is, well, due to this layering, you get some additional slack because you can consider the vertices which are in layers which you currently don't process and which are only processed later. You can consider them as just not being there. So basically, they virtually reduce your uncolored degree for the sake of executing this color trial. So they make your degree smaller, and this gives you some virtual slack. And also these dense vertices get some slack from this additional color reduction. And all of this combined implies that you select that vertices here have is in the order of their external degree. And once you have this, the external degree goes down fast. And the crux here is really that inside the almost click, there are no conflicts. For the outside world, it really just looks like each node tries a random color from their list. This is why the same analysis as for this two data coloring applies here. So let me tell you a bit of how do we implement this synchronized color trial here, that there are no conflicts. So what was being done before by Harris, Schneider, and Su is the following process in local with a slightly different click decomposition, but very similar. You just have a leader in each almost click. And these almost clicks have very small diameters. I usually think of diameter 2. Then this leader learns all the lists of all the vertices in the click, learns the whole communication graph, the graph structure induced by such an almost click. And then the leader processes the vertices greedily in an arbitrary order, and it just picks a random color from the list for a vertex, afterwards updates the lists of all the neighbors in the almost click of this vertex, and then continues with the next vertex, and again picks a color random from the colors that are still remaining for this vertex. And all of this is done locally inside the leader, and once it has determined a color for each of the vertices of the click, it just sends these samples to the vertices, and then they can actually try them in the real graph and get in touch with what that other almost clicks do. But in the CONGEST model, we cannot do this. We cannot learn the lists. It's too much information in the leader. And we cannot learn the graph induced by an almost click. It's also too much information. Instead, and it's going to be a bit involved, what we do is we first build a communication overlay for each almost click. So for people that know the congested click, this is very similar to the congested click, and it's a congested click on roughly delta nodes. So each almost click will be like a congested click, which allows you to actually send quite a lot of information to the leader without interfering with and getting into contact with too many communication issues. And now we deal both of these problems, that we cannot learn the lists and we cannot learn the graph topology. First, each node just samples enough colors from their own list and only sends these samples to the leader. And what we show is that this is sufficient. Even stronger, what we show that it's sufficient that the leader doesn't even know the graph of this almost click. It can just assume that it's really a click and everyone is connected to everyone, and still it works. So this is everything I want to say about this. So here we have full algorithm again. We compute the ACD decomposition. We create slack for vertices. The slack generation gives slack to sparse vertices. It gives slack also to dense vertices. Then we color the sparse nodes by just trying colors uniformly at random, 3 colors. We afterwards color the small degree vertices by using the Barenboim et al. Framework, which also, this log delta prime term here, also just tries colors uniformly at random. And only in the post-shattering phase here, we rely on deterministic algorithms to color the small connected components. And then we color the dense nodes, where we process each almost click by layers. And then many of these almost clicks are processed at the same time. And when dealing with one layer, we just repeat for log delta times these synchronous color trials, which very quickly bring down the degrees between different almost clicks. And once these are down, basically one further round brings degree down within the almost click, which leaves us also here with a small degree subgraph of uncolored nodes, which we then color with the Barenboim et al. Framework. So this is the whole algorithm. Thank you. Let me just finish with one slide of what happened after our paper and some open questions, but I won't say anything further about this slide.